And going to kind of talk about what an area function is first of all. I'm not going to go through too much of the theory on here, but just kind of give you a little bit of an idea of geometrically what the fundamental theorem is doing. Okay, so what we're trying to do is we're trying to find an area under a curve. So we're doing an integral from a to x, and then this is some function like that. Okay, so it turns out that we've talked about what everything represents in here. Is this really gives you what we call an area function, a of x, and the idea is we're getting that area under the curve. That's what we've talked about. All this is saying is we can think of this integral as a function that represents an area. So you can go from any point you want to if you have a function. If you wanted to find that area from a to b, then your integral would just go to a to b like that. Okay? We know how to do an integral. That's an antiderivative. But then we're going to evaluate that a and b. That's what I'm going to show you how to do here. Okay? So here's the fundamental theorem. The next page is kind of talking about this. And the idea is basically this. You have an area function on a continuous interval a to b. And the idea is this. If you take the derivative of this area function, you would also take the derivative of this integral, and then you would get the function back. Okay, now here's the way to wrap your head around this. If you had something like this, okay, like on the test you did last week, you did antiderivatives, right? Do you have the ability to tell you're right on an antiderivative?
Yes.
Absolutely. So if you did this antiderivative right here, you'd have x to the third over 3 plus c, correct? By power rule. Well, how do you check your answer? You take the derivative, right? Okay, that's what I want you guys to understand is what this statement is saying. So if you did that, you would have 1/3 times 3x squared. Of course, the derivative of c is 0. That takes you back to the beginning, correct? So that's what this statement is saying is, yeah, this is an equation. You can take the derivative of a, you can take the derivative of an integral, but when you do take the derivative of an integral, you get that function back. Does that make sense? Okay, that's the idea behind that. That's the technical talk of that. So here's what the fundamental theorem says. This is the big thing, and this will tell you how to now evaluate what's called a definite integral. Okay? So we know that what we're doing with a definite integral is you have a continuous function, and you're finding an area under a curve from a to b. Okay, first of all, capital F is an antiderivative. So it turns out what you do is you do the antiderivative and you evaluate it at b. That means the antiderivative is a function and you can evaluate it at b. Then you take the antiderivative and you evaluate it at a and you subtract the two, and that gives you the exact area under the curve. That's the idea. Now I'm going to try to show you on the next page geometrically what that means, because I want you to at least wrap your head around why you subtract those two values. Okay, like that. Okay? So the idea, this is all just terminology we've talked about. This is the integrand. Dx is the differential, which represents the width of the rectangle. And then capital F is the antiderivative. That's the notation. You're going to see me do this all the time. We're going to get an antiderivative. I usually put a bar to represent that I'm going to evaluate that antiderivative from a to b. Okay? Okay, now what I'm going to try to show you, and I'm not going to go through the theory on this too much. This is for you to read up on a little bit if you want to. My goal today is to kind of get you through the geometry of this. So I want to see if this makes any sense to you. All right, so the idea would be if you had, say you have an integral, I'd like you to at least write this one little thing down on this page. Okay, let's say that we're doing an integral from like a to b or something like that of some function f of x. All right, and let me stand up so I can kind of show you what's going on with this kind of thing here, right? The idea is if you're doing a definite integral, like from a to b, say that's a b, okay? What you end up doing on this is to get that area, here's what you have to do. You have to integrate all the way from 0 to b, then you got to integrate from 0 to a, and then subtract the result. And I'll show you in a different diagram that'll probably help a little bit. But if you're finding that area here, you'd have to find the big area from there to there, right? Then you'd have to find that little area from there to there. Does it make sense if you took the big area minus the little area, you get the leftover?
Right.
Just tell me if that makes sense. That's, yes. At this level of class, that's the best way to explain why you do that f of b minus f of a. All right? That's the idea. Because you're doing an area function, and so you have to do it in that order. The big area minus the little area like that. Okay? Okay. Now, let's go ahead and let's look at doing some of these problems. Now, what we're going to do now is I'm going to show you how to actually do this with it. And we don't have to look at the graph, although I'm providing a graph on some of these examples. Okay, so this is a definite integral. So what we're going to do on this now is you're actually finding the area of this region. And that's not a region that you know a formula for. Okay, like a parabola, there's no formula you learn in high school about that. You have to know calculus to find that area. So what we do is we do the antiderivative first. So let's go ahead and do the antiderivative. Okay, what's the antiderivative of 60x? 60x squared over 2. Okay, power rule, right? Okay, what's the antiderivative of 6x squared? Right, power rule. You're going to do that a bunch, right? Add 1 to the exponent, divide by the result. So when you do that, you're going to have, that's going to go to 30 x to the second, like that. This is 6x to the third over 3, so that's going to go to 2x to the third. So you start by doing your antiderivative, okay? Then what you do is you put this bar like that, and then you put a 0 and 10. That's just a notational system that we use, okay? Then what we do is we do f of b minus f of a. That's what the fundamental theorem says to do. So what we're actually doing is we're doing evaluating the antiderivative at 10, evaluating it at 0, and subtracting the result. Okay, so that's what we're going to do. Go ahead and let's plug in the 10. So we're going to go 30 times 10 to the second minus 2 times 10 to the third, like that. So that's your f of b part. Then we plug in the 0. It's always nice when you have a 0 too, because it usually makes it easy. So we're going to do 30 times 0 squared minus 2 times 0 cubed, like that. So that's the arithmetic you work out to get the exact area under that curve, okay? All right, well, we'll work a little bit. You can use your calculator a little bit. Sometimes the arithmetic gets a little messy on these too. So that's going to be 30 times 100 minus 2 times 1,000. So what that is. And on this side, can you guys see that everything's going to go to 0? And anytime you see that something goes to 0, you can do that in your head. Because that'll happen actually a lot of times, is if you're going from 0 to something. Not always, but a lot of times that thing goes to 0. Okay, so what we're going to have then is this is 30 times 1,000 is 3,000. That is 2,000. And of course, this thing here is 0, so it looks like the exact area under that curve is 1,000. Okay? That's pretty fascinating, too. I mean, I don't know if it is to you, but the fact that calculus and just basic ideas with a derivative can find that perfect area right there with precision. That's it. Okay? All right, get your calculator out if you brought it. I think I already showed this to you, but I'm going to remind you of this one more time. Your calculator can do this. We'll do this a couple of times as we're going over this. Just your calculator can be used and your calculator approximates. Sometimes it'll give the exact value. Sometimes it'll give an approximation because it doesn't really do an antiderivative. Your calculator isn't smart enough to do that. It just does a formula kind of in the background. So, okay, so with this one, let's put in the function. Don't put in the derivative. Put in the function, which is 60x and minus 6x squared. So you want to get that put in. For the window, just make the window like the graph I gave you. Okay, just exactly like that. Just go 0 to 10. That's because we're integrating from 0 to 10. And you can scale that by 1 or 2. That's your call. It doesn't make any difference. Okay, and then let's go like from 0 to maybe 150. Just follow exactly what the graph has. Okay, scale that. Let's do it by 30, just the same way that the graph did, that I gave you did. Okay, like that. So that would be your window. Then what you want to do is you want to go ahead and graph that. Okay, once you have that in, and it should give you that same curve. And I'll just remind you of how you do this. So make a note of this if you need to. What you do is you go to second, and then trace. Whoops, calculator keeps disappearing. Let me fix that real quick. Okay, so we just go second trace. And when you do that, you go option 7, which is the integral. Okay, and that option 7, you put the lower limit in, which is 0. That's the lower limit of the integral. Press enter. You put in the upper limit, which is 10. Then you do this, and what it's attempting to show you, the idea is, think of that as an infinite number of rectangles that are infinitesimally skinny, like that. Now, your calculator isn't doing an infinite. It may be doing 1,000. I have no idea. But it's doing a bunch of them, okay? So look at that. It got 1,000, like that, okay? Pretty cool, isn't it? Okay? You can use this to check definite integrals. So it's kind of a good tool to know how to do. And it'll be really helpful in Calc 2, because Calc 2 is all about integrals. The first half of the class is like integrals like crazy, and it's really good to know how to do that with your technology. Okay, everybody got that okay? Okay, that's very helpful. Okay, let's do this next one, okay? Now, if we look at this, we are going to go ahead and just work it out. You may already know what the answer is. Do you think you have an idea what the answer might be? Okay, just might be. What do you think? Okay, let's go ahead and work it out. So what we're going to do is you can bring the 3 out. That's a good starting place. So that would be 3 times the integral from 0 to 2 pi of sine of x dx, like that. Okay, that's how you start. Okay, now what is the antiderivative of the sine x? Yeah, be careful. It's negative cosine x. Okay, anytime that you do an antiderivative, you need to check it and make sure you do. You don't need to finish this problem until you know that that's right. So take the derivative in your head, and that would give you a sine x, right? Okay, that's important. Now, don't forget about the 3 also. That 3 is there, so I'm going to write that as 3 times negative cosine x, and then we usually put a bar and evaluate that from 0 to 2 pi. Okay, now what you can do when you're doing a definite integral, if you have a constant with your antiderivative, you can just bring that out of the evaluation. So it's probably best to write this as negative 3 cosine x 0 to 2 pi. You don't need to have that constant inside of that evaluation. Just at the end of the problem, multiply by negative 3. So what we're going to do is we're going to do negative 3. Now we do our fundamental theorem. The fundamental theorem says do the antiderivative at the upper limit and then subtract the antiderivative at the lower limit. That's what you do. So you're going to do cosine of 2 pi minus cosine of 0, like that, and then you work out the details. And let's see if we don't in fact get 0. So here's how this works out. So that's negative 3. The cosine of 2 pi is 1 if you look it up on a unit circle. Cosine of 0 is also 1. So as we predicted, we got 0. Okay? And why was that? Because the areas balanced each other out. That's the idea. Okay? That's what made that happen, basically. All right? Okay? And I'll tell you what actually happens on this is this area right here is 3. This area right here is negative 3. That's how it happens. Okay? So if you did that integral from 0 to pi, you would actually get 3. All right? Does that make sense? Does that seem logical? Okay? All right? That's mainly what we're going to work on. There's a lot of different illustrations of this. I want to do some things that have some graphs in it first of all. Okay, let's take a look at this one. Now, sometimes your antiderivative will be a little bit more difficult. This one right here, if you do this antiderivative, the first thing, what do you want to do probably with that square root? Make it a 1/2 power, just like you're doing a derivative, okay? You also probably want to break that up. So you want to say that's t to the 1/2, but you can split this up into two parts. You could say t to the 1/2 over t to the first minus 1 over t like that. Okay, you got to do it that way. You need to split it up into two parts. Now you can subtract the exponents here. So I'm going to just write this as t to the 1/2 over t to the 2/2. Okay, getting a common denominator. You can subtract those exponents. So that would be t to the 1/2 minus 2/2. So that would be t to the negative 1/2 power. Now I haven't even integrated yet. I'm just trying to get it ready to integrate. So what I'm really going to do is I'm going to do the integral of t to the negative 1/2 minus 1 over t dt. And I'm not going to worry about the limits until I get that antiderivative. That's the idea. Everybody with me there? And why I did that? Okay, I did that basically because I can do the power rule on that. And what would be the antiderivative of 1 over t? That's a logarithm, right? Okay, the derivative of ln t is 1 over t, right? So that's one you can do in your head. So this one is a power rule. So you do that, you add 1 to that. So I'm going to add 2/2. And then you divide by the result. So negative 1/2 plus 2/2 is 1/2. Okay, I'm going to write that out, but you're going to divide by 1/2, so what are you really going to do? You're going to multiply by 2, okay? Then this antiderivative is ln, and be sure you use absolute value t there. That's important, okay? So what you'd end up getting then is 2 t to the 1/2 minus ln t, and then I'm going to go ahead and change this back to 2 times square root of t minus ln t like that. Okay, what I just did is I got the antiderivative, okay? That's what capital F of t is. So that's the antiderivative. That's going to be the function that's going to allow us to find our area. So what I did there is something that you did like in section 4.9. You did some of that on your test, right? Okay, so now what we're going to do is we go ahead and we basically take this antiderivative and we evaluate it from 1/16 to 1/4, okay? And we're going to find that area under the curve. Okay, let me ask you a question before I finish this up. Would you expect when we do when we get this answer, are we going to get a negative or a positive? Negative. You're going to get a negative, okay? Don't let that surprise you. That's okay. All right, so let's go ahead and put this together and see what we get then. So we're going to do, first thing is plug in the 1/4. So you're going to have 2 times the square root of 1/4 minus the natural logarithm of 1/4. Okay, that's the upper limit. Now subtract and then plug in the lower limit like that. So you're going to do 2 times square root of 1/16 minus natural logarithm of 1/16 like that. Okay, so that's how that goes. All right, then to finish this up, we got to do the arithmetic. The part of these problems that sometimes is messy is the arithmetic. So you got to kind of get used to that. Sometimes these problems are easy to do arithmetic. Sometimes they take a little bit of work. So let's go ahead and see where we can get with this one. So this is, the square root of 1/4 is 1/2. Okay, natural logarithm of 1, there is something that we could do on that. Now the absolute value of 1/4 is 1/4. So we don't need that absolute value anymore. And then we'll talk in a minute about what we're going to do with that. Okay, then we go to the next one. The square root of 1/16 is 2 times 1/4. And then same thing here, that's just logarithm of 1 over 16 like that. All right, so we got a little bit of basic simplification that we can do. And you got to kind of pay attention to these logarithms when they show up. Okay, so what's going to happen is that's going to cross out. So that's going to give me 1 minus. Now I'm going to put a parenthesis here, and I'm going to do this like this. How do you break up a log of a fraction? That's a difference, right? You say ln of 1 minus ln of 4. Now you better have that in parentheses because you got a subtraction symbol there. You got to pay attention to little things like that. That's important. Then on the next thing, I'm going to do the same thing. Okay, 2 over 4 reduces to a half. Okay, so that's going to be 1/2 there. Then I'm going to do exactly the same thing with this. I'm going to break that up as ln1 minus ln16 like that. All right, everybody with me there? Sometimes the hardest part of these problems is the arithmetic, not the calculus necessarily. All right, let's see what happens. Let's see if we got any cancellations. So this is 1. The ln of 1 is what? 0. That shows up all the time. Then I have minus ln 4. Okay, then I go to this one. I've got a half. Okay, minus. Oh, I made a mistake there. You guys see the mistake I made? Plus, okay, that's plus. Minus, minus. I go here, that's a half. That again is a 0. Okay, then that minus, minus is going to be plus ln16 like that. Okay, now there's a couple other things I can do. So I'm going to take off these brackets now. So this is just 1 plus ln4 minus, and be careful with the sign, that's minus a half, and now that's going to be minus ln16. Okay, like that. Now, there's one thing I can do with that 16. Any idea what I could do with that 16? I can write it as what? You could do 4 to the second. There's a reason for that. Because I see that ln of 4 there, and then you can change that to 4 to the second. Okay, you can do that. Okay, so what I'd have is this. Now, 1 minus a half is a half. Those go together. Those are like terms. Then I'm going to write this as ln 4 minus ln of 4 to the second. All right, the reason I did that is because now what can you do with that 2? Bring it down, and then you have some like terms, say. So you have 1/2 plus ln 4 minus 2 ln 4. Okay, then what you have on that is you have, these are like terms. See, that's 1 ln 4 and 2 ln 4. So you'd have 1/2 minus 1 ln 4. Okay, that's the answer to the problem. Okay, now you got to be really careful with those brackets and parentheses on that, but that's what you get into when you do definite integrals. That's the part that you may struggle the most with. Okay, because the antiderivatives that you do in Calc 1 are a lot more basic than they are in Calc 2. Okay, does that make sense what I did? You guys see the arithmetic okay? Is there anything I need to clarify on the arithmetic? Okay. That's going to be a standard thing you're going to do on logarithms a lot of times, is you got to put those together, break those up like that when you do that. Okay, you could check your answer graphically. You could put that in your calculator, do exactly what I showed you to do on that, and you could compare it to this exact answer. That's the best way to learn how to check and verify answers, is to do it with technology. Okay. Okay, let me explain a couple of things on these next 2 problems. And let's see, then what I want to get into here a little bit is just kind of do some examples, a little bit more repetition of some definite integrals. So let's go ahead and let's draw a graph of f of x equals c. Okay, now c is a constant. So what would a graph of f of x equals a constant look like? It'd be a horizontal line, right? Because it's kind of like we're doing something like f of x equals 2, something like that. So let's just kind of draw a little picture that's really f of x equals c. Okay, that would be, some value c like that. So what we're doing is explaining why an area function is an increasing function. Well, first of all, if we integrated from like 0 to 1, okay, well, you would have this area right here, right? Okay, that would be the area like that. What if we integrated from 0 to 2? Well, then we would have a bigger area, right? So the idea is when you're doing this, when you're doing a definite integral, you're really doing an area function, and that area is going to get bigger as you go out further. Do you agree with that? Okay, that's the idea, is the area just gets bigger from 0 to infinity as you're going out like that, okay? That's the idea, is the further you go out on this function, the bigger the area is going to get. So it's going to increase always, right? Does that make sense? Okay. All right, let's do these two integrals right here. And these are two pretty simple integrals. And we want to kind of see what we get on this then. Okay, and you'll probably do maybe around 2 or 3 definite integrals on the final. So you want to definitely know how to do these kind of things without the graphing and everything. All right, so what I'm going to do on this one is, first thing, you can bring out the 3. That's an important thing to learn about integrals, is you can take constants out, or you can just ignore it and do the antiderivative and do it that way if you want to. Okay, this one should be pretty easy. Tell me what the antiderivative of x to the second is. X to the third over 3, right? Power rule. Okay, so you write down the 3, then we have x to the third over 3, and you're going to evaluate that from 0 to 2. Okay, this shouldn't be that hard to do. All right, so let's go ahead and do that. So we'll have 3. Now, the first thing you're going to do is plug the 2 in. So you're going to have 2 to the third over 3. And you're going to plug in the 0. It's always great when your teacher gives you 0 there because it makes it easy most of the time. Okay, so finish it out. That's going to be 3. That's going to be 8/3 minus 0. Okay, so that's just 3 times 8/3. So the area, not 18, is 8. Okay, that's how that goes. All right. Now, if you don't understand anything on the arithmetic, just pause me. Sometimes when I get this arithmetic, I start whipping through it because it's arithmetic. Okay, but if you need me to clarify anything, just let me know. All right, anybody have a question with that? Okay, that's not too bad. Now, the next one, we're going to do the same thing. See, we already have the antiderivative. This is the same integral, except the limits are different. So the idea with this is it's just going to be 3 times x to the third over 3. Now we're going to go from -2 to 2 like this, okay? I'm going to go ahead and get it, and then we'll kind of talk about the answer. I'm halfway curious if anybody knows what the answer would be without me finishing.
0.
Not 0.
It'll be 16.
16, good. How come?
If it's -2 or +2, it's going to have the same outcome as the square.
Probably. How come?
Because there's no shift in the graph.
It's a parabola, right? Okay. And the thing is, that parabola is always above the y-axis. What you would find if you put this in your graphing calculator, I'll tell you exactly what you would find. You'd have a parabola that goes like that. Now, what's going to happen is we just found the area from 0 to 2. Okay? Well, now all you're going to do is get another area that's the same, and you're going to double it. Does that make any sense? Okay? I can tell you were thinking correctly on there, so that's the idea. Okay? The graph will kind of open that up. So let's see if we don't indeed get 16. Okay. All right. So we would have 3. Now we're going to plug in the 2. So that's going to be 2 to the third over 3. And then minus. And then -2 to the third over 3 like that. Okay. Remember, when you're doing fundamental theorem, that area function, you're always subtracting those results. Okay. So let's see if we do get 16 out of this then. So that's going to be 3 times 8/3. Minus, and see, that's going to be -8/3. Okay, so it doesn't cancel, so you'd end up getting 3. That becomes plus, so that's 16/3. So, as we predicted, you got double the area. So you can take advantage of those sometimes. This is basically an even function. That's an even function, so you can double the area. So you can do it that way if you happen to see that, so it's kind of nice to see stuff like that. But if you don't, you can crunch out the details, and it works out beautifully. Okay, so is there any question about how I'm doing these definite integrals? Okay, so you see, mostly it's antiderivative and arithmetic. That's what you're dealing with. Okay, let's do a couple of more things here. I want to run through a little bit more with this before we take a break. Let's look at this graph here and go through these things. So these are area functions. Okay, this is a area function. So this is representing an integral. So when we do a of negative 2, this problem here, we're not going to work the integral out because we don't know the function, but we do have a graph and we have some areas given. So what this is going to mean is you're really going from negative 2 to x. See, in this area function, x is the upper limit of integration. So that means a negative 2 is going to go there. So we're going to work that out. Do you know what the answer to that is? Just like boom? Zero. Everybody got that? Why 0? The limits are the same. So you know what would happen? You would have a rectangle, one rectangle, that would be infinitely skinny, so it would have 0 area. That's the idea. If those limits are the same, it's always going to work out that way. And the reason is because you're going to have this. You're going to do the antiderivative and evaluate it at negative 2. And then you're going to do the antiderivative and evaluate it at the same number. You're going to get 0, right? That's why. Okay? All right, let's look at the next one. The next one's f of 8. Okay, so I've given you a different area function here. Okay, so when I do this now, what I'm going to have is I'm going from 4 to 8, f of t dt. Okay, the only way you're going to figure this out is just look at the graph and see what I got. Well, let's see. If we go from 4 to 8, we have that. What's going to be the answer? Is it going to be 9 or negative 9? Negative 9. That's because it's below the curve. Okay, everybody got it? Okay, all right. Okay, next one, a of 4. Okay, so we're going to go to this point. A of 4, again, go to this first integral. So you're going to go from negative 2 to 4 of f of t dt like that. Negative 2 to 4. So let's see if we can put this together. So it looks like you've got the area right there. This is what we're looking for in this problem is that. So we should have enough information. Is that going to be positive or negative? Okay, so it looks like what they gave you, if I'm interpreting this right, it looks like the area from here to here is 8. The area from here to here is 17. So if I'm looking at this correctly, that's 8. That's 17. So we would just do what? 8 plus 17 to get 25. That's it. Okay? Okay, then the last one, we got f of 4. So you go to the integral I've got in red there. So it's going to go 4 to 4. F of t dt, what's the answer to that one? 0, like that. Okay? So that's an exercise to just make sure you understand how to interpret the meaning of the definite integral and the geometry behind it. That's it. Okay, nothing to work out really. Okay, let's do this, this 25. Then after this, we'll take a break. I will pass your tests out and give you a little time to look at that. This one right here, probably a pretty good type of thing that you could see on your final. A pretty straightforward antiderivative with doing the limits of integration. A definite integral, you don't have the plus c. You get a definitive answer. Okay? So, antiderivative, what's that? X to the third over 3. Next one, what's that? X squared over 2. How about this one? A lot of you didn't do so hot on these on the test. 6x, okay. You take a derivative to see if you're right. You got to know those antiderivative rules, okay. So we're going to go from negative 2 to 3 like that, okay. If you're doing your final exam, I would highly recommend just take 30 seconds to find out if your antiderivative is right. Then proceed, okay. All right, now we're going to move on. Evaluate at 3. So we're going to have 3 to the third over 3 minus 3 to the second over 2 minus 6 times 3. Okay, all I'm doing is just plugging in. Everywhere I see an x, I plug in a 3. Now subtract and then do the negative 2. So now we're going to do negative 2 to the third over 3 minus negative 2 to the second over 2 minus 6 times negative 2. So again, it's just a ton of arithmetic you got to do on these problems, okay? All right, so let's see what we have. We'll have 27 over 3 minus 9 over 2 minus 18. That's going to be negative 8 over 3 here minus 4 over 2. And then a negative times a negative is a positive 12b. Okay, just be extremely careful with the details, right? And let's just see what we have here. So this looks like 9 minus 9 halves minus 18. I don't really need the parentheses anymore. I'm going to go ahead and just change the signs. Okay, you can do this in a different order too. So it's like plus 8/3 plus, let's see, that's a 2, and then minus 12. Okay, so I'm just doing simplifying fractions, basic arithmetic stuff. Okay, so let's see what we have. Now these things right here are all like terms, so we can put all that together. So that looks like negative 9 plus 2 is what? Negative 7 minus 12, that should be negative 19 is what that is, okay? So that takes care of that. Then you got to get a common denominator on this. So that's going to be 6. Okay, so I'm going to change this like this. I got to multiply this by 3 over 3. That's going to give 27 over 6. I got to multiply this by 2 over 2. Okay, so that's going to be plus 16 over 6 like that. Okay, and it looks like that's going to be negative 19. And then if you do negative 27 plus 16, that looks like minus 11 over 6 like that. I probably could have got a common denominator on the whole thing. I don't know why I didn't do that, but let's go ahead and do it now. So I'm going to put that over 1, multiply by 6 over 6, and we'll see what we get. And then I think we'll do I'll show you how to do a quick check on the calculator on this one. Negative 19 times 6 is going to be negative 114 over 6 minus 11 over 6. So that's negative 125 over 6. And that's the way I want you to write the answer. I don't want decimals. I just want a reduced fraction like that. Okay? All right, now let's see if I got that right. Because sometimes on arithmetic, I just go real fast on it and I make a mistake somewhere, but I think I got it. Okay, if you want to do this with me, let's do this. I'm going to put in x squared, then minus x, minus 6. And if you want to check this definite integral, just set your window up. I'm going to go like 0 to 3. You could also go negative 2 to 3. It's usually better, though, to go a little below and a little beyond. There are times when you'll get errors depending on what the integral is. If you just go your window negative 2 to 3, it'll mess up occasionally. So I recommend maybe we just go like, say something like negative 5 to 5. Whoops, got that backwards. I'm just making the interval a little bit bigger than the limits. Okay, so I'm going to go like negative 5 to 5. Scale of 1, and I have no idea what the y values are. This is what I usually do. I usually go second graph to get the table to come out, and I just sort of scan through and see what kind of values I have. It looks like I have some negative values, and I got like a 14 in there, so I'm going to do something like this. So for the y window, let's go, let's do like negative 20 to 20. Something like that, and then maybe scale by 5 or something like that, okay? I'll slide that over there if you need to see that. Okay, now just type graph. Okay, it should be a parabola. Now we went from negative 2 to 3. So does it make sense to everybody that why we got a negative answer? Yeah, we have that region of the parabola. Now you can go second calc, option 7, lower limits negative 2, upper limits 3. And now this is not kind enough to give you the exact answer, but you can use this to check. So it's giving negative 20.83 and repeating 3's like this. So what you could do is you could take our answer, which is negative 25 over 6, and see if they're the same. Hey, success. Okay, we did it. Okay, that's the idea. All right, so I would recommend you know how to use that to check. That will come in real handy on these kind of things. Okay, so let me get your, what we want to do with this one, first of all, is let's bring out go ahead and bring out the 2. So we got 2 times the integral 0 to pi over 4, cosine x dx. Okay, I want to do a couple of things with trig. Okay, so this one's pretty straightforward. Okay, what's the antiderivative of the cosine? the sine, because the derivative of the sine is a cosine. So you'd have 2 times the sine, that's your antiderivative, and we're going to evaluate the antiderivative from 0 to pi over 4. Okay, like that. Okay, so when we do this then, when you're doing fundamental theorem, you're going to do sine of pi over 4, and then minus sine of 0 like that. Okay, so you got your antiderivative, same idea. This one's pretty straightforward, okay? All right, so what's the sine of pi over 4? Square root of 2 over 2, right? Sine of 0 is 0, like that, all right? So it looks like what you get is you get 2 times the square root of 2 over 2, so you get 2. Square root of 2, sorry. Okay, so that's the precise area under that curve. All right, so if you're what's happening on that is, one thing I want to kind of mention on this is really representing like from 0 to 45, like this 45 degrees, that area turns out to be square root of 2. So one thing that'll happen on this is every time that you go through a 45 degree increment on a cosine, it'll have a square root of 2 as the area, and of course some of it will be negative because it goes below the x-axis, right? So that's the idea. That one's pretty straightforward, okay? Should be anyway. Okay, how about the next one? Do you guys know what the antiderivative of square root of 1 minus x squared is? Have you ever seen that?
Inverse sine.
That's inverse sine, okay? So you got to know those derivative rules in order to do the antiderivative. Okay, so the antiderivative is going to be inverse sine of x, and then we're going to evaluate that from 0 to 1/2. So you have to work with inverse trig functions a lot. You'll do this a lot in Calc 2. We use the inverse tangent and inverse sine quite a lot in integrals. So what we'd do now when we evaluate, we'd have inverse sine of 1/2 minus inverse sine of 0 like that. Okay, now it just goes back to trigonometry stuff, and there's a few things that you got to remember on this. The range of an inverse sine is like real important that you remember this stuff. Okay, do you guys remember what I mean by that, or what that is? Negative pi over 2 to pi over 2. Okay, see, when you're doing this, you can't just get any place on the unit circle where the sine is 1/2. You have to be within this range, which is negative pi over 2 to pi over 2. Okay, those are things that you want to review from time to time. Like the inverse cosine, you might want to write this down if you don't remember this. The inverse cosine, its range is 0 to pi. Okay, so if you're doing that, you have to pay attention to that. Okay, so what this would be is on a unit circle, on an inverse sine, you're either going to give a positive answer in quadrant 1 or a negative answer in quadrant 4. The place where the sine is equal to 1/2 is at the point root 3 over 2 comma 1/2. In radians, what is that? Pi over 6. Okay, either look it up on the unit circle or create that unit circle. That's why we're so big in trig at making students memorize the unit circle, because it just keeps showing up. Okay, and then the inverse sine of 0, the only place on the unit circle within that range would be at 0. So you get that. So that means the answer to this problem would then be pi over 6. That's the exact area under that curve.
Can you go over how you got that pi over 6?
Yes, okay. First of all, when you're doing an inverse sine, what you're doing is you're looking backwards on a unit circle. So on a unit circle, if you look at your basic points, you have square root of 3 over 2, 1/2. Okay, the sine is the y value, right? Okay, so if you're doing an inverse sine of 1/2, you need to know what angle gives you that value of 1/2. That angle, the angles go like this. This is pi over 6. Pi over 6 is 30 degrees. This would be pi over 4. That would be pi over 3. That's what I'm doing. But you have to fall within that range. Okay, you have to be there. Okay, that's the idea. All right, anybody else have a question about that? Okay, and you want to do that in your head. You can go through, I mean, you can do this. If you go through, if you're in radian mode on a calculator, you can do this. If you go inverse sine of 0.5 of a half like that, well, it's not going to give you that gives me a degree answer, and then you can change that to radians. I mean, I want you to be able to do that in your head, but you can check with your calculator on that if you want to. Okay, let's do a couple others. I want to do one with an E, and then I think I'll finish up with this page, and we're going to move on to 5.5 where I can teach you use substitution. Okay, so this one we're going to move out the 10. That's a constant, so that's always kind of a good starting point on an integral. And we do have a rule for this. I think this showed up on your test. You either knew the rule or you didn't know the rule. The rule for an antiderivative of e to the kx is what? 1 over k e to the kx. Okay, you need to know that because that shows up all the time. And in higher calculus, it'll show up constantly. You need to know it like immediately. So this antiderivative will then be 1/2 e to the 2x like that. Okay? And then what you're going to do is you're going to evaluate from 0 to 1. Okay, like that. All right, now see this stuff right here, that's just a constant. So you could reduce that 10 over 2 to 5. And then all you got to do is just evaluate the antiderivative from 0 to 1. I always recommend to make your arithmetic easier, if you got a constant, just pull that out, evaluate your antiderivative, then multiply by 5. It's easier that way. Okay, now what we do is we just plug in the 1. So we have e to the 2 times 1 minus e to the 2 times 0, like that. So that's going to be 5 e to the 2nd minus e to the 0. Now we want to get an exact answer. We're not getting decimals, so what you just do is write this as 5 times e to the 2nd minus 1. Okay, you could do a distributive property if you want to, but you don't have to. So I'm just going to say either answer is acceptable to have that or to have that. That's it. Okay, that one again is pretty straightforward. Okay, when you get to Calc 2, these integrals are going to be a lot more challenging than this. We just try to get you comfortable with the simpler antiderivatives in this level of class. And like I say, Calc 2, about the first half of it, you'll just do integrals like crazy. All right, so that's what you got to look forward to. And integrals are a lot harder than derivatives. They really are. All right, let's do this last one here. Now this one, the only thing that you could do at this stage is just to multiply that out. Okay, a lot of times students have the idea that, well, I could just integrate x, I could integrate x minus 2, I could integrate x minus 4 and multiply together. It doesn't work. Okay, you can never do that. There is no product rule for an integral. Okay, there is something that we call integration by parts that you learn in Calc 2, which is analogous to the product rule. But for now, there isn't anything you can do except just multiply this out. So let's go ahead and just do that. Now, the way I'm going to do this is just FOIL that. So when I FOIL that, I'm going to have x squared minus 4x minus 2x plus 8. And then I'm going to multiply the x through like that. So that's x times x squared minus 6x plus 8. So that's going to be x to the 3rd minus 6x squared plus 8x like that. Okay? That's why you would do this integral. I mean, there wouldn't be any other thing you would want to do on this integral. Okay? So let's go ahead and write down, we got integral 0 to 4, and we're doing the integral of x to the 3rd minus 6x squared plus 8x dx. Okay, like that. All right, so what we need to do from here is just do the antiderivative. This should be hopefully a real basic one to you. What's that? That's x to the 4th over 4. Next one, 6x to the 3rd over 3. And the next one, 8x to the 2nd over 2. Power rule is going to keep showing up. And then that whole thing gets evaluated from 0 to 4. Okay, like that. Okay? So, what I want to do on this, there's a couple of things I can reduce. Like that reduces to 2. So I'm going to go ahead and write this just as x to the 4th over 4 minus 2x to the 3rd plus 4x squared, and then integrate from 0 to 4. I like that. The rest of it's arithmetic. Everybody with me okay? Okay, so be sure that if you have to multiply something out, you gotta do that. Okay? All right, now we go ahead and plug in the 4. So we're gonna have everywhere you see an x, just plug in the 4. And we do that first, so that's gonna be 4 to the 4th over 4 minus 2 times 4 to the 3rd plus 4 times 4 to the 2nd. Then plug in the 0. Now, here's what you can do. I don't care if you do this. Can you guys see, tell me, if you plugged in a 0, wouldn't that whole thing just go to 0? So I don't care if you just do that, okay? Because that'll happen a lot. Now, don't fall for that. Sometimes it doesn't go to 0, so make sure it goes to 0 before you do that. But take advantage of that if you see that. Saves you a little bit of time, okay? So now what I would have is 256. 4 to the 4th is 256. This would be 2 times 64. Then that would be 4 times 16 like that. So let's see. 256 divided by 4, I think, is 64. That's 128. And then that's 64. So I think that's 0. So what does that mean if it's 0? Probably means symmetry, right? Okay. Now I'm going to show you one other thing on this problem. That's kind of good to show this to see if you remember something from college algebra. So I'll just show you something on this. Okay, the places where if you take this equation and you set it equal to 0, this would actually give you where your intercepts are. So what you would have is you would actually have an intercept at 2, an intercept at 4, and an intercept at 0. Okay, and this is a cubic function. We multiplied this out and got a cubic function. I think the way this graph probably works is it probably does something like that. I'm pretty sure it goes like that if you put that on a calculator. And actually what happened is this area and that area ended up balancing each other out. That's the idea. Okay, so if you did that on a graphing calculator, I think you would see that. That's the idea. Okay? Okay, so what do you guys think of definite integrals?
Wonderful.
Definitely fun, right?